Well, good morning, Seven Blue. Happy Freya's Day. We're going to double lesson it, and I have a special surprise, which I'll let you know at the end. So L116, 117, we're going to be looking at division by zero and then significant digits. First of all, the most important takeaway from this is that division by zero is what we call undefined. And that's an important concept. Basically, if you're ever in a position where they're asking you to divide by zero, stop the presses and write undefined. We just simply can't do it. This lesson is meant to help you understand why. So here's something we could think about. So if we had a number line, we put 0 here, let's put 1 here, and -1. And then obviously we can break that stuff down even more. So if I was going to go decimal on it, like I think about boom, 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 and on the other side, boop, 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 boop. And so if I was starting to do problems, say, like take the number 10 and divide it by something like 1. 1, I think we'd have to say is pretty close to 0 as far as it goes, you know. Think about maybe money that people earn, how much more that is than 1, and therefore 1 is very close to 0 as far as it goes. To get even closer to 0, what if I was to take 10 and divide it by that? Well, we know that would be 0.1, right? And to even push it further, which I'm not going to draw out, what if I was to divide 10 by 0 and 100, 0.01? Now I'm getting closer and closer to 1 each of my divisors. Now on the flip side, we also have this -1 concept, which is pretty darn close to 0 when it comes out to it. So if I was to take 10 divided by -1, let's say, or push it a little bit closer to 0, like that, 10 divided by -0.1, getting closer to 0, right? Each of my divisors getting closer and closer. How about 10 divided by -0.01? Oh, I'm almost there, right? And that could go on for days. And that idea that it could go on for days, let's notice what will happen to our actual, what are our quotients in this situation. So when I think about this 10 divided by 1, I know it's 10. Then when I go 10 divided by 0.1, well, wouldn't that be 100? And then what about 10 divided by 0.01? Well, that would be 1,000. And on the flip side over here, 10 divided by -1, clearly -10. And see how my quotients are getting further and further away from 0, right? Further and further and further away. In fact, if we were to kind of graph this out, what we'd see on the positive side is it would graph in this sort of manner, like that, going on forever and further and further away from 0. If we were to graph the negative side, it would actually look like that. And this idea helps us to kind of understand that as my divisors get closer and closer to 0, what happens to my quotients? They get further and further away. How far away? Well, technically or theoretically, we could say that they move toward what we call positive infinity. If I kept getting closer and closer to 0, I would get towards infinity. We actually have a symbol for infinity. You may have seen it before. It's like an upside down figure 8. Not upside down, but flipped over. Upside down would look the same. Okay, what about over here? What's happening with as I'm getting closer and closer to 0 with my divisors? Well, yeah, I'm getting further and further away from 0. Towards where? Well, towards not positive infinity, but towards negative infinity. And that idea kind of helps us understand why dividing by 0 is just impossible. It's not something we can do. Now, another kind of fact that might help is what we grew up with called fact families. So we know fact families would be something like 4 times 2 is equal to 8, and 2 times 4 is equal to 8. And then we could do that other side of it, the division side. So 8 divided by 4 is equal to 2, and 8 divided by 2 is equal to 4. These are called fact families because these are all facts, right? The way that the inverses work with each other, right? The division is the inverse of multiplication. And so all of those are facts. But if I tried to do it with 0, so let's take something like 2 times 0. Well, we know that's equal to 0. And if I flip that around, 0 times 2, that's equal to 0. Now, what about this? What about 0 divided by 2? What's that equal to? Yeah, 0. So everything's working fine, except for what about this? 2 divided by 0 is equal to 0? No, it's not. That's not true. That is just blatantly not true. Hence, the idea of dividing by 0 doesn't fit within our concept of truth and facts and fact families. So here's the thing, kids. You just simply can't divide by 0. Now you're like, well, where does this go? Well, one place that it goes is something like this. So let's write this down. It says y equals 12 over x plus 2. And if we think about like our concepts of functions like x and y, I know we've named that the x is our domain and the y is our range. And so they'll sometimes ask you, they'll say, hey, what limitations are there on the domain, or what is the domain? And so it becomes an act of kind of naming what it's not. So one way to think about this is if I can't end up with zeros, I could take my expression here, this x plus 2, and I can make it equal to 0. And then, obviously, I would subtract 2 on both sides and end up with x equals negative 2. But that x equals negative 2 is actually what it can't be. Because if I plugged in negative 2 for that x, then what I'd end up with is negative 2 plus 2, which is 0. And I'd be dividing by 0. And that is undefined. It's not allowed. So I'm actually doing this little x plus 2 equals 0 to make a statement that x cannot be negative 2. It can be anything else, any other number, but it can't be negative 2. And that's a truism, and that's something that we want to kind of push forward. In fact, all the stuff that was talked about, this screen would actually be the most important. I hope you're ready to write. This is not my surprise. My surprise comes at the end of the video, but I hope you're ready to write. We've got a lot of writing to do, and I don't blame me. I blame science. We're going to explore something called significant digits, which is something for science. In fact, I'm sure Mrs. Bush would love to hear you talk about this. Do I love this? Oh my gosh, it is so weird to me. But whatever, let's do it. So one thing we want to talk about in significant digits is things we call counts and measures. So a count is exact. Like if we were going to name the number of students in 7 Blue, that is an exact count, right? There's a specific number and it is exact. So counts are exact, yes? Measures, however, so if I was to measure someone's foot or someone's height or anything like that, a measure is simply, it's not exact. And it all comes down to a degree of precision. You know, am I measuring them to the closest foot, to the closest inch, to the closest half inch, to the closest quarter inch, the eighth inch? It goes on and on and on. And so when we think about measuring something to like a really precise degree, well, at some point we'd have to say, well, I don't know. I don't have measurement tools that help me with that. So when dealing with measurements, we want to think about this, that the number of digits we use to express a measure, and I'm just going to tell you this first one, we say a measure with confidence. Again, can I confidently measure someone to the nearest foot? Absolutely. Nearest inch? Yeah. Nearest half inch? Nearest quarter inch? Nearest eighth? Whoa. Nearest 16th? I don't know if I can. And then we haven't even thought about the nearest 32nd. And then there's like, and how many decimals? So if I say, 4.5 centimeters. Okay, maybe. How about 4.55 centimeters? Well, I don't know. 4.555? I don't know. Like, I don't have tools for that. So the number of digits we use to express a measure with confidence is called the number of, yeah, you guessed it, the number of significant digits. And again, this is not the big writing. In fact, the big writing's about to start. I hope that your hand is limbered up. Please, let's write down the rules to significant digits. And then we're going to talk about a problem they may ask you to deal with. So the rules are this. You are, number one, you're going to always count the non-zero digits. Number two, you're going to count the zeros between non-zero digits. Number three, you're going to count trailing zeros in the decimal number. Number four, do not count zeros if there's not a non-zero digit to the left. Number five, trailing zeros of whole numbers are ambiguous. And then number six, exact numbers have an unlimited number of significant digits. Who came up with this? Scientists. I know math is a science, but this is, again, if you're at the end of this going, I have no idea what just happened, I really encourage you to find a scientist and let them help you with it. So given this, we're going to look at A, B, C, and D. We're going to state the number of significant digits. So the first one says the diameter of a quarter is about 2.5 centimeters. So let's focus on that. So 2.5. So if I look at my rules, it says count the non-zero digits. Well, those are non-zero digits. So 1, 2, And that would be it. I would just say there's 2 significant digits there. All right, next one. It says, a ruler is about, so we're going to focus on this one. A ruler is about 30.5 centimeters long. Okay, so I count the non-zero digits, so that's 3 and 5. I'm at 2. Oh, it also says I should count the zeros between the non-zero digits, so that 0 I count. So I'd have to say 3. This is where it gets a little weird. So the Earth's distance from the sun is about 9.3 times 10 to the 7th miles. So again, we know from the first that we count the non-zero digits. So we're looking at that 9.3. So I'm at 2. Count the zeros between non-zero, there are none. Count trailing zeros in a decimal number. Well, this isn't going to be a decimal number. Do not count zeros if there's not a non-zero digit to the left. Trailing zeros of whole numbers are ambiguous. Okay, I think that's the thing that we're talking about here. So again, surprisingly, this, even though this would go out to about 93 million, this only has 2 significant digits. Again, ask a scientist. Last one. Okay, so a mile is 5,280 feet. That is an exact number. And if we go all the way down to number 6, it says exact numbers have an unlimited number of significant digits. So I'll answer unlimited. And you might go, what? And I'd go, totally. All right, let's see if there's something else we can latch onto here. Okay, write this down. It says a product or quotient of 2 measurements may only have as many significant digits as the measure with the least amount of digits. This one I can kind of get behind. So let's say they wanted to take a measurement of 8.9 centimeters and break it into 4 equal parts. So in order to do that, I would take 8.9 and I'd divide it by 4. And we know how to do this work, so obviously we're going to lay our decimals. 4 goes into 8 twice, 2 times 4, 8, subtract, bring down, 4 goes into 9 twice, multiply through, 2 times 4, 8, subtract, tag a 0, bring it down, 4 into 10, yep, I'm going to extendo 2 times 4 is 8, oh, when will this ever end, tag a 0, 20, 4 into 25, 20 minus 20, blah, blah, blah. And that is our exact number. However, this is how this works. Think about what it says. It says it can only have as many significant digits as the measure. Well, what was our measure? It was 8.9, which only has 2, right? This only has 2 significant digits. So my product or quotient, in this case a quotient, can only have 2 as well. So even though I know it's exactly 2.225 centimeters, I'm going to call it just simply 2.2 centimeters. And I can kind of get behind that one. Yeah? Let's try another idea. Similarly, it says a summer difference may show no more decimal places than the measurement with the fewest number of decimal places. So, okay. Then they give us an example. The test tube contained 6.24 milliliters of liquid. After heating, it contained 4.6 milliliters. How many milliliters evaporated? Okay, I get this. So this would be, I'm subtracting here. So I would take the 6.24, and I'm going to subtract it by my 4.6. I'll tag a 0. I know how to do this. And I'm going to place my decimal. Oop, I didn't. Whoops. I'm going to borrow 5, 12, 6, 1. Oh, there's my decimal. Okay, so 1.64. Yeah, sounds good to me. 1.64 milliliters exactly. However, notice what it says. It says a sum or difference. So this is a difference. May show no more decimal places than the measurement with the fewest number of decimal places. So my measurements were 6.24 and 4.6. Well, 4.6, that guy only had 2. So guess what? My difference in this case can only have 2. So even though I know it's exactly 1.64, I'm just going to call it 1.6 milliliters. And again, looking at those rules, there's some that I'm like, I have no idea what you're talking about. But when they give me these examples like these and this, I can kind of get behind that. I hope you can too. But really, it's a science thing, not so much a math thing. Okay, so what's my special surprise? Hey, I know it's Freya's Day, and I know throughout your life with me, I never give you homework over the weekend. However, I do give 8th graders homework over the weekend, and you guys are so knocking on the door being an 8th grader, and I need to give you this homework just so you can kind of feel like an 8th grader and just so we can stay on track to finish this book. So I am going to ask you over the several days you have, because we do have a day off on Monday, but I need you to come back on Tuesday with this homework done. So we are doing the split. I know it's not normal. Please understand. HW116 evens, 117 odds. Have a great weekend. Bye.